In this video, we will talk about different ways of calculating concentration. So, concentration, what is it? Well, concentration is the amount of solute per quantity of solvent. And we can actually express this in a variety of ways, such as the mass of our solute in the volume of our solvent, the mass of our solute in the mass of our solvent, volume of solute, and volume of solvent. We can also express this as parts per million, parts per billion, and the one that'll be most relevant for us and the one that we'll come back to the most is molar concentration. So when you're working through this, you have to be careful and watch for the terminology that's provided between solute, solvent, and solution, and you need to be able to distinguish between each one. So getting into the different types of concentration that we have, the first one that we'll deal with is the mass volume percent. With mass volume percent, it gives the mass of solute dissolved in a volume of solution, and this is expressed as a percent. It's also referred to, at least written-wise, as M/V, and that obviously just stands for mass volume percent. Formula that you'll use to calculate mass volume percent is provided in the following box. So for mass volume percent, this is equal to the mass of the solute, and that mass of solute should be in grams, divided by the volume of the solution, and that volume should be in milliliters. Because it is a percent, we multiply it by 100. Let's have a look at a sample problem using mass volume percent. So in the following problem, we have a pharmacist that adds 2.00 milliliters of distilled water to a 4.00 gram of a powdered drug. The final volume of that solution is 3.00 milliliters. We're asked for the mass percent volume of this solution. In your question on the sheet that you have, you'll see 3 questions, A, B, and C. Cross out A, we won't deal with that, and we'll only deal with B and with C. So in question B, we're asked what is the percent mass per volume of the solution. And then in question C, we're asked what mass of drug is needed to make a 10.0 milliliter solution. So we'll start with question B, determining the mass volume percent. So that for that mass volume percent, within this, we're going to need the mass of our solute. So in this case, it will be our powdered drug. So it's the thing that we're dissolving. So we have that 4 grams. And that's going to be divided by the volume of the solution. And we're told in the question that that final volume is 3 milliliters. And we are going to multiply that by 100%. So when we do the calculation, we end up getting a mass volume percent of 133%. And yes, it can be more than 100. Just go with it. In part B, in part C, we're asked what mass of drug is needed to make a 10.0 milliliter solution. We know that the mass volume percent of our drug is 133%, which we calculated from our previous question. Within this, we're being asked to figure out what mass of drug we need, so we'll label that as X. And the volume of solution that we want is a 10 milliliter solution. And of course, this is multiplied by 100. So when we rearrange and solve for X, I won't go through the various steps, but we should get a mass of drug needed as 13.3 grams. And don't forget our therefore statement. So therefore, we can say mass of drug needed is 13.3 grams. And in our final answer, we also have 3 significant digits, which should line up with the amount of significant digits in the question. In the next type of concentration calculation, we deal with mass percent. So mass percent gives the mass of a solute divided by the mass of a solution. And this too is expressed as a percent. It's also referred to also as the mass percent as well. So formula for calculating mass percent is provided in the box here. So again, this is the mass of our solution in grams, or mass of our solute, sorry, in grams, divided by the mass of our solution, also in grams. And we're going to multiply that by 100%. So where we normally see this is with the concentration of alloys. Those are mixtures of different metals, and they are usually expressed as a mass percent. So in the following problem, we have 55 grams of potassium hydroxide is dissolved in 100 grams of water. We're asked what is the concentration of the solution, expressed as a mass percent. So for that mass percent, it is going to be the mass of our solute, which we're told is 55 grams. So it's that potassium hydroxide that we're dissolving into water. And we need to divide that by the mass of the solution, of the total solution itself. So when we have that final solution, it is going to take into account the mass of the water plus the mass of the potassium hydroxide that we have dissolved in that water. And of course, multiplied by 100. And no, the 55 grams will not cancel out. Remember that we're adding in our denominator, and this will not allow us to cancel out those numbers. So when we go ahead and start to simplify this and start to solve for it, we'll have 55 grams divided by 155 grams, which is the mass of our solution, multiplied by 100. That mass percent we end up solving for will be 35%. And our final answer has 2 significant digits because the 55 grams has 2 significant digits as well. In the next type of concentration calculation, we have volume percent. Volume percent gives the volume of solute divided by the volume of solution, expressed as a percent. Now, equation for calculating volume percent is the following. So it is the volume of the solute in milliliters divided by the volume of the solution in milliliters, again multiplied by 100. So in the following sample problem, we have rubbing alcohol that is commonly used as an antiseptic for small cuts. It is sold as 70% volume per volume solution of isopropyl alcohol in water. And we're asked what volume of isopropyl alcohol is used to make 500 milliliters of rubbing alcohol. So in this particular question, rather than figuring out what our percent volume is, we have to figure out how much of the rubbing alcohol we need to make a 500 milliliter solution. So we're going to assume that we want a 70% solution. So we know we'll need that 70%. This is equal to the volume of isopropyl alcohol, which we need to solve for, divided by the volume of the solution that we want to make, which in this case is 500 milliliters. And this, of course, is multiplied by 100%. And when we rearrange and solve for x, we determine x to be 350 milliliters. If we wanted to take into account significant figures, we would have to round accordingly then, and we'll round up. And to have an appropriate number of sig figs, then the volume of isopropyl alcohol that we would need would be 400 milliliters, according to significant digits. That's where it kind of gets a little bit weird, because suddenly we're adding more than what we need. In the next type of concentration calculation, we start to get in parts per billion and parts per million. The reason why we use parts per million and parts per billion is that it's used to express very, very small concentrations. It's a lot easier to say parts per billion or parts per million than to say 0.00000000001%. And with parts per million and parts per billion, it is a mass-mass relationship, but instead of multiplying by 100, we're either going to multiply our answer by 1,000,000 or by 1,000,000,000. So with parts per million, it is the mass of the solute, again in grams, divided by the mass of the solution in grams. And this is all now multiplied by 1,000,000 rather than 100. So instead of putting it in a percentage by multiplying it by 100, if we multiply it by 1,000,000, this puts us in parts per million. With parts per billion, it's the same thing. Mass of the solute in grams divided by the mass of the solution in grams. And this time we're going to multiply it by 10 to the 9 or by 1,000,000,000. When you plug this into a calculator, when you're doing this calculation, when you reach the times 1,000,000 part, what you want to do is, in your calculator, you want to enter that in as 1, hit the exponent or that equivalent button on your calculator, and then hit the 6. And that will be 1,000,000 on your calculator. Or you can just multiply it by 1,000,000 and type in all those zeros if you like. So let's look at the following sample problem. So symptoms of mercury poisoning become apparent after a person has accumulated more than 20 milligrams of mercury in the body. We're asked to express this amount as parts per million for a 60 kilogram person, and then to express this amount as parts per billion. On the page that you have, you'll have a part C to it. Just cross that out, we're not going to do that. So on your page, it should just be part A and part B. So for part A, where we're asked to express this amount as parts per million for a 60 kilogram person, before we go and do this, we have to be in units of grams, so we need to do a little bit of unit conversion. So our 20 milligrams, we do need to convert that into grams. Remember that if we're converting into units of grams, for every 1 gram, we will have 1,000 milligrams. So we are going to divide by 1,000. This will give us 0.02 grams in that necessary unit. We also have the 60 kilograms, which we also need to convert into grams. And remember that for every 1,000 grams, we have 1 kilogram. So our units of kilograms will cancel out. And we take our number, we multiply it by 1,000, and we'll get 60,000 grams as the mass of that person. So now that we have our masses converted into the appropriate units, we can go ahead and determine that concentration in parts per billion. So we take the mass of our solute, which in this case is going to be the mass of the mercury, which is 0.02 grams. We divide it by the mass of our solution, or mass of our solution, which in this case will be the person itself, so divided by the 60,000 grams, and we multiply this number by 1 million. And what we should get when we take into account significant digits is a mass of 0.3 parts per million. In part B, we're asked to convert or to express this amount as parts per billion. So for those parts per billion, it's going to be the same calculation that we just did. So that 0.02 grams divided by the 60,000 grams for the mass of that person. But instead, this time of multiplying it by 1 million, we will multiply it by 1 billion. And when we do that, we get 333.33 parts per billion. And if we were to put this into the appropriate amount of significant digits, we would have to round down, and we would get 300 parts per billion. No decimal at the end. In the last type of concentration calculation that we'll talk about, this is the one that's going to be most relevant for us and the one that we come back to the most as we go along in the solutions unit. So this deals with molar concentration. We come back to our good friend, the mole. So with molar concentration, it's the number of moles of solute that can be dissolved in 1 liter of solution. So molar concentration, and we abbreviate that moles per liter, is going to be the amount of solute expressed in moles divided by the volume of solution in liters. So our molar concentration, which we'll indicate by a capital C, is going to be equal to the number of moles divided by the volume of the solution in liters. So we end up with moles per liter. Sometimes you might see this referred to as molarity. Molarity is an old convention. We now refer to it as moles per liter. And molarity is sometimes referred to as a capital M. Again, that's old convention. We now just use moles per liter. So in the following sample problem, we have a saline solution that contains 0.90 grams of sodium chloride, it's NaCl, dissolved in 100 milliliters of solution. What is the molar concentration of the solution? So right now, our amount of sodium chloride is given to us in grams. We need to be able to convert that into moles. So we're going to bring back in some equations and some calculations that we talked about in the previous unit. So we'll bring back in our good friend for calculating number of moles, where number of moles is equal to mass divided by molar mass. In this case, we know our mass of sodium chloride is going to be 0.9 grams. We can easily figure out the molar mass of sodium chloride, which will work out to be 58.44 grams per mole. We take our two numbers, put them into the appropriate spots in our equation so that we have the 0.9 grams divided by 58.44 grams per mole. We work that out to be 0.0154 moles of sodium chloride. And now that we know the number of moles of sodium chloride that we have, we can go ahead and figure out the concentration of the solution. So for the concentration of the solution, we are going to use that C is equal to N divided by V. We're going to take the number of moles that we just calculated at 0.0154 moles of sodium chloride, and we're going to divide that by the volume of the solution in liters. So we have to take that 100 milliliters, we divide it by 1,000, and that gives us a volume of it'll be 0.1 liters. And when we do that calculation, we get a concentration of 0.154 moles per liter. If we take into account sig figs, we'll have to round up, and so our concentration will be 0.2 moles per liter. So that does it for the concentration calculations. Please work on the following questions. So each of these goes through the different concentration calculations that we talked about. If there are some that you feel that you're okay with, then you don't need to do them all. If there's some that you feel you need more practice with, then there's more questions in the textbook that I didn't list on the page. So please ensure that you complete these questions, and of course solutions and answers can be found on my website under the textbook solutions.